At the end of our last class period, we were talking about the behavior of comparators. And we're going to begin today by looking at a simulation for a comparator, the details of which I've already posted on YouTube, but we can quickly review what's going on. So I have a sinusoidal input that is ranging from -5 volts to +5 volts, and it is being applied to the non-inverting input terminal of my op-amp circuit. I have a reference voltage of 2 volts, which is the input signal is being compared to, and my expectation is that whenever Vin is greater than 2 volts, I should observe that my output voltage is at VCC plus, which is 5 volts, and whenever my input voltage is less than Vref, I should see that my output voltage is at VCC minus, which is -5 volts. So I'm going to go ahead and click the running man icon here, which will give me the plot to verify this operation. So I'm going to plot Vin and Vout on the same graph. I'm going to adjust my axis limits so that I can see more clearly that I'm actually hitting plus and minus 5 volts for my output, and that's exactly what I get. So for Vin is greater than 2 volts, this portion of the green curve, I see that my output voltage is at +5 volts, and whenever Vin is less than 2 volts, this portion of the green curve, I see that my output is -5 volts. Now, I'm going to make a small modification to this circuit to include the effects of noise, because this is going to show us a limitation of the behavior of the comparator device. So I'm going to close my plot, go back to my schematic, and I'm going to model my noise using a behavioral voltage source. Behavioral voltage sources, which you can find by typing in BV into the component window, is LT-Spice's version of a voltage-controlled voltage source, or really just a voltage source that depends on some function. So I'm going to put my behavioral voltage source in. I'm going to wire it in series to my original input signal. I'm going to label it, as V in plus N, so it will be my input voltage, my sinusoidal input voltage plus this noise source with respect to ground. And finally, I'm going to right click on the behavioral voltage source and edit this equation, where I'm going to write white so that I'll get white noise, and I'm going to do 2e to the 6 multiplied by time. And so this is going to just create random values for the noise voltage that's going to be applied to my signal. So I'm going to click OK, and I am going to now also delete this Vin that's being applied to my non-inverting input terminal and replace that with Vin plus N, so that I'm applying the noisy input signal to my non-inverting terminal. If I run my simulation again, let's look at Vin. We get a nice even sinusoid. And the reason why it's lagging a bit is because it's processing what these random values are, and that takes the computer some time to do. If I click on this node, I'm going to see the noise superimposed on top of my input signal. And so I see that my input signal is fairly noisy. It's probably tens to hundreds of millivolts being applied on my input signal. And now let's look at the output. So my output voltage signal, it's behaving roughly how I would expect. meaning when things are definitively above 2 volts, I'm getting an output of 5, and when things are definitively below 2 volts, I'm getting an output of -5. But I have these thick red lines here around where Vn is equal to 2 volts. So I'm going to zoom in, as it were, on one of them by right-clicking on my horizontal axis. I'm going to choose to start looking at 0.3 seconds, finish looking at 0.6 seconds, and let's change my time division to be 20 milliseconds. Click OK. And so I could get a little bit of a better picture of what's going on now. Effectively, what's happening is when I have noise around my reference level, my output is swinging wildly from VCC plus down to VCC minus until I get well under the reference voltage level. So the comparators then are very susceptible to a noisy input signal, and this can be problematic for several applications. A way to rectify this is to use a positive feedback comparator circuit, better known as a Schmitt trigger. So I'm going to go ahead and close this plot and then show you how to implement the Schmitt trigger. I'm going to delete this Vn plus N input signal from this non-inverting terminal because I'm going to create a feedback loop that connects my non-inverting input terminal to my output, and in that feedback loop I am going to place a resistor. I'm going to choose, just for the sake of argument, that this resistor will be a 3 kilo ohm resistor. I'm also going to apply another resistor, so I'm just forming a simple resistive network. Let's make this guy a 1 kilo ohm resistor. And this terminal here is where I'm going to apply my input voltage now. So let's apply Vn plus N. And run our simulation. So if we look at our input voltage and our noise, and now we look at this output, we can see that we no longer get those weird thick vertical lines. What's happening is that whenever my input voltage exceeds what's called my upper trigger limit, my output is swinging from negative VCC to positive VCC, and whenever my input gets less than my lower trigger limit, I observe that my output swings from positive VCC to negative VCC. So I'm going to plot V out just as a function of V in, and this will give us a little bit more insight as to what I was talking about. So this graph is what is commonly known to as a hysteresis graph, okay? And so what that means is that this circuit effectively has a little bit of memory. So what's happening is as my voltage goes from -5 volts and increases and increases and increases, at some point I am going to exceed my upper trigger limit, which is going to cause my voltage to swing, my output voltage to swing positive, and it's going to stay positive. And then when my voltage starts decreasing, I'm going to stay at VCC plus until my input voltage falls below my lower trigger limit, at which case it abruptly drops back down to VCC minus, and this cycle just repeats over and over and over. So this begs the question, how are we going to determine what our upper and lower trigger limits are? And the answer is that they're based largely on what the power supply voltages are, as well as what the resistor values are in the circuit. And we're going to take a few moments to analyze this circuit and develop a mathematical relation for that next.